everyone, welcome to this lecture. In this lecture, we start crystal field theory. In last lecture, we have discussed about VBT, that is valence bond theory. This crystal field theory is the another theory to explain the bonding in complex compound. Okay, and this theory is developed by H. Bethe and V. Blake. They are scientists which have developed this theory was developed by these two scientists. This theory explains nature of bonding between metal and ligand, some properties of coordination compound, just like magnetic property, spectral property, which which can't be explained on the basis of VBT. VBT have some failure, and VBT, that is valence bond theory, has some failure, and on the basis of that, this theory was developed by these two scientists. Okay, then come to main features or postulates of this crystal field theory. The bonding, according to this theory, the bonding between central metal ion and metal ion or atom and ligand in any complex is electrostatic. This theory considered that the bonding between, that is interaction between metal and ligand is purely electrostatic. It means the ligand considered as a point charge in this theory, and the positive charge is present in any metal ion. Okay, and there will be interaction between them, that is simple electrostatic attraction between them. Okay, as we know, the central metal cation remains surrounded by the ligands, and ligands carry one or more lone pair. That is definition of ligand, that is ligand must carry lone pair which can be donated to the metal ion, and this central metal ion considered as a positive point charge and ligand considered as a negative point charge in this type of this theory, right? Example, this is the ligand, this is the metal ion which is considered as positive charge, and the ligand present around this positive charge acts as a negative point charge, and there will be interaction between them. Okay, there is total electrostatic interaction between metal and ligand, and if this ligand is neutral, just like this, then it acts as a dipole, right? And this negative end of dipole is attracted towards metal ion, right? It means this ligand are considered as a point charge in safety, and neutral ligand considered as a dipole. That is, negative end of dipole is attracted towards central positive ion. Okay, for example, this chloride ion, bromide ion, CN ion, these are negative ion ligands. In this case, ion-ion interaction takes place. But in the case of NH3 ligands, H2O ligands or CO ligands, ion dipole interaction takes place. These ligands acts as a dipole, and negative end of this ligand is attracted towards positive charged metal ion. Okay, then come to second point. As we know, the d orbital present in the metal ion may be of two types. There are 5 d orbital: dxy, dyz, dy, dzx. Okay, and then another d orbitals are dx square minus y square and dz square. These are the 5 d orbitals present in central metal ion. And in these d orbitals, 2 d orbitals are axial d orbitals. You can divide these d orbitals into 2 parts, that is axial d orbital and non-axial d orbital. It is divided, these d orbitals are divided on the basis of structure of the d orbital. These are the representation of this d orbital. This one is dxy, dxz, dyz. These are the 3 d orbitals. These are non-axial, and these are dx square y square and dz square. What is difference between them? These are non-axial d orbital because lobes of these d orbitals not present along the axis. In this case, lobes are present in between x and y. In this case, lobes are present in between x and z. In this case, it will present in between y and z. But in this case, these are 2 axial d orbital because in this case, lobes of d orbitals are present along the axis. In this case, it is present along the x and y axis. In this case also, it will present along the z axis. Okay. These are 5 orbital, and on the basis of structure, it can be divided into 2 parts, that is, these 3 are non-axial d orbital and these are axial d orbital. And it is very much important to explain the crystal field theory. In the free metal ion, these d orbitals are similar in energy. All these 5 d orbitals have same energy. They may call degenerated d orbital having similar energy. Okay. These axial d orbital oriented along the axis, non-axial oriented in the region between the axis, but in the free metal ion, in the absence of any ligand, these d orbitals are degenerated, that is having similar energy, just like p-orbital. Okay. We know that pxy, px, py, pz, these 3 orbitals are degenerated, having similar energy. In the same way, in the free metal ion, these 5 d orbitals are degenerated. Then come to next point. When some ligands are present in surrounding, when some ligands are present in surrounding of metal ion, then under influence of such type of spherical symmetric field, the negative charge present around the metal ion and it can provide symmetrical field of negative charge around this metal ion, and due to this the energy of d orbitals of metal ion increases uniformly. Due to presence of ligand around it, the d orbitals of the metal ion the energy of d orbitals of the metal ion increases, but it will increase uniformly. It means after this increasing, that is, all d orbital remains degenerated at higher energy. It means at higher energy also they are degenerated. It means they have similar energy, same energy. Okay. The energy of d orbital increases due to electrostatic repulsion between electrons of d orbitals and electrons of ligand. If ligands are present around this metal ion, then repulsion takes place between electrons of d orbital which are present in d orbitals and the electrons present in ligand. And due to this repulsion, the energy of d orbitals will increase but uniformly. It means they remain degenerated at higher energy. Okay, it is first step. Okay, when it is present in ligand, symmetrical ligand field, energy of d orbital will increase. Then, when the ligand approach to the central atom ion along a specific direction, when these ligands approach to the central metal ion along the specific direction to come to form the complex having a definite geometry, right? If they approach to the metal, then they can approach through a particular direction. They can't approach haphazardly. They can approach to the particular direction so that they can maintain geometry. They can form complex of definite geometry. That is maybe tetrahedral, maybe octahedral, etc. Then d orbital splits into two groups. When ligands approach to the metal ion on a point of definite geometry, then d orbitals splits into two groups of orbital having different energy. Why that so? It is because when ligand approach to the geometrical position, then electrons or d orbitals experience repulsion by lone pair of approaching ligand, due to which energy of d orbital increases, and d orbital having different orientation. We know that these are the d orbitals. These two are axial d orbital, in which electrons of d orbital present along the axis. In this case, electrons are present in the lobe. What is this? It is the area where probability of finding electron is maximum. That is orbital structure. And if these electrons are present in this case, the d orbital in between the axis, then due to different orientation, these d orbitals experience different interaction from the ligand. The orbitals lying in direction of approaching ligand experience greater repulsion. If ligands approaches to the metal ion in the direction of these orbitals present, then this orbitals experience greater repulsion. And when orbitals lying away from the approaching ligand experience less expression. These are the two cases. If these ligands approach to the metal along the orbitals, then this repulsion will be more, and the orbital experience greater repulsion. And if orbitals lying away from the approaching ligand, then it experience less repulsion. Okay, and due to this, the splitting of these 5 degenerated d orbitals into two sets of orbitals. Okay, due to experience of different amount of repulsion, these axial d orbital and non-axial d orbital split into sets of orbital having different energy. It can split into different energy. Okay, and this energy, splitting in a given ligand environment in a complex is called crystal field splitting, right? In a given ligand environment in a complex of a definite geometry is called crystal field splitting. It is this splitting due to repulsion between ligand and metal ion. Okay, and the gap between those sets of orbital is called crystal field splitting energy. You can understand this one with this presentation. This is the representation of d orbital. This one is representation of d orbital in free metal ion, right? These are the 5 d orbitals, axial and non-axial, which are degenerated. It means at the same energy. Okay, when the ligands are present around the any metal ion, then the energy of these d orbitals will increase but symmetrically, but uniformly, and after increasing they remain degenerated. Okay, this first stage is degenerated 5d orbitals in a free metal ion. Okay, these all d orbitals have same energy. And second state, it is representation of 5 degenerated orbitals at higher energy, when the metal ion surrounded by uniformly spread negative charge of ligand, that is in symmetrical negative field. In that case, energy will increase, d orbital's energy will increase, but symmetrically, it means uniformly. They remain degenerated at higher energy. Okay, then come to third stage. This is the stage of crystal field splitting, when any metal ion approach to the geometrical position around the metal ion, when any ligand present around the metal ion approach to the metal ion to a particular geometrical position, that is maybe tetrahedral position, maybe octahedral position, then splitting of these d orbitals takes place. Why? Because if ligand approach along the d orbital, then that d orbital experience more force of repulsion, and when this ligand approaches to metal ion away from this d orbitals, then that d orbitals experience less force, and due to this degenerated d orbitals splits into sets of orbital having different energy. These orbital having different energy, these orbital having different energy, and the difference between these two will be considered as crystal field splitting energy, and it is denoted by this del. Okay, then come to next point. The electrons are filled in splitted d orbitals, that is electrons are filled in these splitted d orbitals. Okay, according to Aufbau principle, Hund's rule, and Pauli exclusion principle. Right? You know that. What is Aufbau principle? It means electron will go in the orbital having lower energy first. Then what is Hund's rule? The orbitals having similar energy, in the orbitals having similar energy, the electron will occupy singly occupied in all orbitals before pairing. And in Pauli exclusion principle, what is this? In each orbital, 2 electrons will present with different spin, opposite spin. Okay, then these are the 3 rules. Pairing of electrons occur only when all the orbitals of similar energy are singly occupied. Second one is pair of the electron may present in the any orbital with opposite spin, and electron enters first into the orbitals. It means filling of electrons in these orbitals present at the different energy level follow these 3 rules. Okay, then magnitude of crystal field splitting energy depends upon various factors. This magnitude, that is del, depends upon various factors such as geometry, charge on metal ion, type of ligand, right? These are the various type of factor on which this magnitude of crystal field splitting depends. Then come to factors affecting the crystal field splitting. This crystal field splitting energy depends upon nature of ligand, oxidation state of metal ion, size of d orbital, geometry, etc. Right? Nature of ligand. Greater the power of the ligand, the larger will be crystal field splitting. Okay. The ligand with high negative charge and small size have higher tendency to donate electron, and they produce larger crystal field splitting. The ligand can be arranged in a increasing order of power splitting, that is this arrangement is called a spectrochemical series, and this one is spectrochemical series. These are the weak field ligand present in the starting, and these are the strong field ligand present at the end of series, and these are the intermediate ligand. Okay, these ligand having higher power to splitting. It means the crystal field splitting energy will be higher in these orbitals. Okay, in general, the halide donor having lowest power, that is weakest ligand, and then oxygen donor, then nitrogen donor, then carbon donor. Okay, you can see that fact. Then oxidation state of metal. The metal ion with higher oxidation state can produce larger crystal field splitting. For example, in these two, this is cobalt complex with water. This is cobalt complex with water with oxidation state 3+. In this case, oxidation state is 2+. And in this case, splitting will be higher for this complex. It is because of presence of higher charge on this complex, that is oxidation state in this case is higher. Okay, then size of d orbital. If size of d orbital of metal will be large, then extent of crystal splitting will be large, right? For example, in this complex, that is complex of rhodium, and if you compare it with the complex of cobalt, both have D6 configuration, but in that case this is the 4D element, this is the 3D element. The size of 4D orbitals in this rhodium 3+ is larger than the size of this 3D orbitals of cobalt. In that case, this crystal field splitting energy for this complex will be higher. Okay, then geometry. Geometry is also important. The crystal field splitting energy also depends upon geometry of complex, and crystal field in tetrahedral complex is always smaller than octahedral. It is due to presence of less number of ligand and less repulsion will occur. Okay, then we'll discuss the crystal field splitting in octahedral and tetrahedral in next class. Thank you very much. Have a good day.